Hello everyone, and welcome to the Week 7 Math 2414 review. In this review, we'll be covering mostly differential equations. We'll continue just working through some of those. And first up, we're going to talk about some separable equations. So, not all differential equations are as nice as others. Separable equations are some of the nicer ones, though. So, what is a separable equation? Well, if you'll recall, we have first-order differential equations, which are written in the form dy over dx is equal to some function of x and y. Well, we say that this equation is separable if specifically we can write it as dy over dx is equal to a function of x multiplied by a function of y. Because what this allows us to do is it allows us to write our differential equation in the form dy over g of y is equal to h of x g of x, and then we can simply integrate, h of x dx. And then to solve it, we can simply integrate both sides because each side is now a one variable function. So, for example, if we have the equation dy over dx is equal to x plus 3 over y plus 2, well, I can write this as 1 over y plus 2 times x plus 3. So here this is separable. I have a y function and an x function, which means I can separate this into dy times y plus 2, if I multiply both sides by y plus 2, is equal to x plus 3 dx. And when I integrate both sides of this, I have 1/2 y squared plus 2y is equal to 1/2 x squared plus 3x plus some constant. And this would be a solution to my differential equation. Now, if I really wanted to, I could probably find a single closed form solution. So to do that, I'm going to write y squared plus 4y is equal to x squared plus 6x plus c1. So all I did is I take this equation and multiply by 2. And now I'm going to complete the square on my y. So I have y plus 2 squared minus 4. Now I have minus 4 because when I write out y plus 2 squared, this is equivalent to y squared plus 4y plus 4. But then I need it to equal exactly y squared plus 4y. So I need to subtract my 4 as well because this is equal to my y squared plus 4y. Which means if I'm subtracting 4 from here, I also need to subtract 4 from this part as well. So I have y plus 2 squared minus 4 is equal to x squared plus 6x plus c1, which means that y plus 2 squared is equal to x squared plus 6x plus just a different constant, which means that y plus 2 is equal to the square root. Theoretically, it would be the positive or negative version of x squared plus 6x plus c2. So then y is equal to plus or minus x squared plus 6x plus c2 minus 2. And that would be a closed form solution to my differential equation. But again, this is mostly just algebraic simplification. The key takeaway here is I can separate my original differential equation into the product of an x function and a y function. So this is a g of y times an h of x. A good example of a problem of a differential equation that is not separable would maybe be dy over dx is equal to x plus y. Here, no matter how hard I try, I can't write x plus y as the product of a y function and an x function. It's just not going to happen. If I had a yx plus y, on the other hand, though, I could factor out a y, and then I'm left with a y function multiplied by an x function. So this is separable, this is not. All right, let's go ahead and give you some practice. Solve the separable differential equation. First off, we have xy times y prime is equal to x squared plus 1. All right, I'll give you a couple minutes to work through those. All right, let's go over these. So first off, we have xy times y prime is equal to x squared plus 1. In order to separate this, we need to get all the y's on one side and all the x's on the other. So here, you can just divide both sides by x, and we have y times y prime is equal to x plus 1 over x. Now when we integrate both sides of this, we get 1/2 y squared is equal to 1/2 x squared plus the natural log of x plus c. Again, I could, if I so desired, turn this into a y equals form. To do that, I'm going to multiply both sides by 2. And then take the square root. So again, this is plus or minus the square root of x squared plus 2 natural log of x plus c1. I personally would prefer this one though. Either works though. In the second case, we are not separated yet, so we're going to need to first divide both sides by a plus y. And then divide both sides by tangent. So we have y prime divided by a plus y is equal to 1 over tangent is cotangent of x. Now we can simply integrate both sides. The integral of the left-hand side is simply u substitution. We can let u equal to a plus y. So du is just equal to y prime. So then we have the integral of du over u, which is of course the natural log of u. So we have the natural log of a plus y on the left-hand side. On the right-hand side, cotangent, we're going to want to break down into cosine x divided by sine of x. Now, here we can again use u substitution, where u is equal to sine of x, and du is equal to the cosine of x dx. So then this integral becomes the integral of du over u, which is again the natural log of u, which in this case is the natural log of sine of x. And of course, we're going to have our plus. And there you have it. That is our solution. This one might be a bit trickier to put in the standard form. We could still do it if we wanted to, though. Here we would have e to the natural log of a plus y is equal to e to the natural log of sine of x plus c, which is e to the natural log of sine of x times e to the c, which is e to the natural log of sine of x is equal to simply sine of x, and e to the c is a new c value, and of course e to the natural log of a plus y gets us a plus y sine of x c1. So y is equal to c1 sine of x minus a. But again, this form also works as well. Now, if you wanted to double check that this is a correct solution, we would want to take the derivative. So this would become c1 times the cosine of x. A is a constant, so it would disappear. And then we would have y prime, so c1 cosine of x times tangent of x should equal to a plus our y. And in this case, our y is c1 sine of x minus a. Now here we have a minus a, so this cancels. Now I'm left with c1 cosine of x. Tangent of x is sine of x over cosine of x. So I can cancel my cosine of x's, is equal to c1 sine of x on this side. So rewriting things, I have c1 sine of x is equal to c1 sine of x, which is of course correct. So we've now written that one in standard form as well. All right. Let's go ahead and move on to the next subject, which is population growth models. We might revisit some separable differential equations later on if we have time. So we talked briefly about population growth models last time because they tend to be a very common application of differential equations, or at least a slightly easier, a more introductory application. Differential equations have lots of applications. Population growth models is just one of the more common examples. So first off, we have two different population growth models. The first is for unbounded population. And in unbounded population growth, well, we can just say that the larger our population is, the faster it can grow because there are more things available to reproduce. So the larger our population, the faster it grows. So we'll go ahead and write that out as the rate of population growth dp over dt is proportionate to the size of the population, where k here is a proportionality constant and p is the size of the population. Now, this is a separable differential equation. I solved it out in the last review, but essentially all we do is we divide both sides by p, and we're left with dp over p is equal to k dt. So integrating both sides tells us that the natural log of p is equal to kt plus c. So then exponentiating both sides gives us that p is equal to e to the kt multiplied by e to the c, or c1 e to the kt. And this is our formula for population when we have unbounded population. You'll often see c written as a e to the kt. So those are our two main equations for unbounded population. We have the differential equation and then the solved form. And notably, in this case, your a value is equal to your initial population. So your population at time t equals 0. Now, unbounded population growth is fairly simple. It's a pretty simple differential equation. You can solve it pretty easily in the general form. Bounded population is a little more difficult, but not that much more difficult. In this case, we say that population growth depends both on the size of the population and how close the population is to the maximum population. So in this case, we have dp over dt is, it should of course be proportionate to the size of the population, but then also the closer it gets to some maximum population m, the slower it should grow. You'll notice when the population is equal to m, we have 1 minus m over m, so 1 minus 1 is 0, and then our dp over dt, our rate of population growth, is 0 if our maximum population has been achieved. So in this case, it's still technically a separable differential equation. Things just get a little trickier. We would have dp over what's technically p times 1 minus p over m is equal to k dt. And this is solvable. We would need to use partial fraction decomposition here to decompose this into two separate components before we can integrate. And if you so desire to do that, you can do it. I'm not going to work it out here, though. Essentially, what we get as our closed form population is that our population is equal to our maximum population divided by 1 plus ae to the negative kt. And again, P is our population, T is our time, K is simply a proportionality constant, which depends mostly just on the problem situation you're working with. It's usually dependent on which species of population, which species you're looking at the growth of. In this case, our M is not exactly equal to, our M is our maximum population. In this case, though, our A value is no longer our initial population. In this case, our A value is dependent on both our maximum population and our initial population. So our A value is a little more complicated, but still not terrible. And these are our formulas for bounded population growth. So let's go ahead and do an example. Let's say we were given the formula dp over dt is equal to 1 over 25 p times 1 minus p over 1200. And we were asked to find a closed form equation for the population. Now I could solve this out because it is a separable differential equation. We could go through and find partial fraction decomposition, or we could recognize this as a bounded population growth model and simply use the solved solution we have here. Now, in this case, I can immediately pull out what k is, because I always have the form dp over dt is equal to k times p times 1 minus p over n. So in this case, this is my k value, 1 over 25. I can also immediately pull out what my maximum value is. So my maximum population is 1200. And now I have all I need to write out my closed form solution. I know that p is equal to m over 1 plus a e to the minus kt, or a is equal to m minus p naught over p naught. I suppose I also need to give an initial population in this problem. So let's just say that p naught is equal to 60. This is also starting information. So I'll put given. Okay. So now we're ready to write out our solution. Because I know that p is equal to m over 1 plus a to the negative kt, I have that p is equal to 1200 divided by 1 plus, now a is going to be 1200, my maximum population, minus my initial population, 60, all over my initial population, 60, which is equal to, since everything is divisible by 10, that's 120 minus 6 over 6, or 114 over 6, which comes out to exactly 19. And for those of you wondering how I did it, I can also do it this way. Write it as 6 times 120 is 6 times 20. So I'm left with 20 minus 1 over 6, and my 6's cancel. That gives me 20 minus 1, which is 19. So my a value is 19. I have e to the, here my k value is 1 over 25, so I have negative t divided by 25. And this is my formula for my population growth. Pretty easy, a lot easier than just going through and solving the integration. All right, time for a couple of quick practice problems. So this first one, write out a formula for the population, and also what is the population after 10 years. I don't need a decimal answer or anything, just give me essentially the value of p at t equals 10. And on the second one, I'm giving you a bunch of initial parameters, and I want to know how much time will it take before my population reaches 4 times 10 to the 7. All right, I'll give you a few minutes to work through those. Good maybe 1 or 2 more minutes. All right, let's go over these. So the first one, it might look a little tricky, but if we factor out a 1 over 50 peak, we actually see that this matches our equation for bounded population growth perfectly. Where here we have a k value of 1 over 50 and also a maximum population, coincidentally, of also 1 over 50. Which means we can go ahead and write our population equation. Again, our A is equal to, excuse me, our A is equal to oh dear, did I not give an initial population here? It looks like I did not. That would make things a little difficult on your end. Okay. So in this case, I think I had an initial population. Let me see if I can find that really quick. I had an A value of 1 over 4, which would make that equal to our maximum population minus B naught over B naught, which tells us that 50 minus P naught should equal 4. So 5/4 P naught should equal to 50. Or in other words, P naught would equal to 25. Okay, sorry. So our initial population was 25, which means that our A value is equal to 50 minus 25. Wait, that's not right. Right, our initial population should have been 40 in this case. 40, okay. So our initial population is 50 minus 40 over 40, which is 10 over 40, which is 1/4. Okay. Right, sorry. So initial population is 40 in this problem. Which would give us a p-value or a population equation of n, our max pop is 50, over 1 plus a, so 1/4 e to the negative kt. So here our k is 1 over 50, so e to the negative t over 50. That is our population equation. Now after 10 years, we have t is equal to 10. So p sub 10 is equal to 50 divided by 1 plus 1/4 e to the negative 10 over 50, or e to the negative 1/5. And again, sorry about that. Our initial population is 40. And that is the last bit of information you need to solve. Okay. In the second one, we have an initial population this time. So we actually can write a population equation. P is equal to m over 1 plus a e to the kt, where a is equal to m minus p naught over p naught, which is equal to 8 times 10 to the 7th minus 2 times 10 to the 7th, divided by 2 times 10 to the 7th. Now we have 8 10 to the 7ths and 2 10 to the 7ths, so that's 6 times 10 to the 7th over 2 times 10 to the 7th, which is 6 over 2, or 3. So my p is equal to 8 times 10 to the 7th over 1 plus 3e to the 0.71 t. Okay. Now I'm looking for when the population is equal to 4 times 10 to the 7th. So I'm going to set 4 times 10 to the 7th equal to 8 times 10 to the 7th over 1 plus 3e to the 0.71 t. Which tells me that 4 times 10 to the 7th over 8 times 10 to the 7th is equal to 1 over 1 plus 3e to the 0.71 t. Now 4 times 10 to the 7th divided by 8 times 10 to the 7th is equal to 1/2. Now this tells me that 2 is equal to 1 plus 3e to the 0.71 t. So 1 is equal to 3e to the 0.71 t, which tells me then that 1/3 is equal to e to the 0.71 t. Now if I take the natural log of each side, I have that the natural log of 1 over 3 is equal to 0.71 t. Now I don't like having a fraction in my natural log, so I'm going to write natural log of 1/3 as the natural log of 3 to the negative first, or negative natural log of 3. Which then tells me that t is equal to the negative natural log of 3 divided by 0.7. And that would be my first time that my population hits 4 times 10 to the 7th. All right. Perfect. So that is bounded population growth. Now the last topic for today is going to be some predator-prey systems. Or, in other words, predator-prey systems usually have 2 populations: predator population and the prey population. And of course, because the predators eat the prey, the predator population is going to impact the prey population. If there are more predators, then the prey population is going to decrease faster. If there are few predators, then the prey population is maybe going to increase instead. So let's kind of think about some of the logic behind this. If we have few predators, then that means that our prey, well, they aren't getting eaten as quickly, which means that the prey population will increase. Well, if the prey population increases, then there is more food available for the predators, which means that the predator population will increase. But now there are more predators, so more things to eat the prey, so the prey population is going to decrease. But now there's not enough food for the predator, so the predator population is going to decrease as well. And we see we get some kind of loop that goes on like this. And what you'll often see this represented as is in a diagram. So if the x-axis is time and the y-axis is population, then what we'll often see is what's almost like a phase shifted diagram. So if here I have a prey population, and its population spikes like this, what you'll often see is that the predator population will lag slightly behind it, like this. So blue would be predator, and then the red would be prey. And whenever the prey population increases, that gives room for more predators. So we have a lot more predators show up as the prey population increases. But then as soon as the prey population starts to decrease, like it does here, well, the predators start running out of food, so they die off as well. And then that gives the opportunity for the prey population to increase again because there's less being. So that if you see a diagram like this, it often means, hey, maybe we have a predator-prey relationship because these things are probably related somehow. And if we wanted to write out some more formal equations, well, if R is our prey and W is our predator population, well, then we could write out that the rate of change of our prey population is proportional, first off, to the size of the prey population, but then we also have to take away based on the size of our predator population. So we increase based on the size of the prey population, decrease based on how many predators there are. You'll notice we're also decreasing based on the size of the prey population as well. That's to also kind of put an upper bound on our population size. Similarly, our predator population is dependent first on the number of predators, but also on the amount of prey available. So whenever we have more predators, there's actually less food per predator. So we have a decrease based on the size of the predator population, but then we can gain more predators based on the size of both our prey population and our predator population. And these equations I'm not quite sure where they're derived from, honestly. You can probably look up the derivation in your textbook, but in general, because this system is complicated, these two equations are related to each other very heavily. You can't solve one without solving the other. In general, you can't find a general solution to these, which is unfortunate, but that's how a lot of coupled systems work. And I guess important to notice is that A, B, K, and little r are all constants. But these are a couple of equations that model our predator-prey relationship. The one last graph we might want to talk about is the phase trajectory graph. Now, the phase trajectory graph is a graph that might be a bit unusual at first, but on one axis we have the prey population, and on the other axis we have the predator population. So, in general, if we start out with a small population of both predator and prey, well, our prey population is going to increase because there's not a lot to eat them. But as soon as our prey population increases, our predator population is going to start increasing, which is then going to cause our prey population to start decreasing. like this. And once we have a lot of predators and not very much prey, well then our predator population is going to start decreasing because the predators can't find as much. And then we end up right back where we started. But importantly, if we start out at some time t naught, we're going to have what's essentially 3 phases. So if this is phase 1, this is phase 2, this is phase 3, well then in the first phase, we have not many predators, so the prey population will increase. In the second phase, we have lots of prey, so we have that the predator population increases, while the prey population decreases. And finally, in our last phase, we have too many predators for the amount of prey, so the predator population decreases. And we're left back where we start. So this is really a cyclic kind of thing occurring. We start out at t0, then we follow along, our prey population is going to increase initially, then we get to a cap, and our predator population starts increasing, so then our prey population starts to decrease. Then we have not enough prey and too many predators, so our predator population decreases, and we're left back where we're started. So over time, we essentially just follow this cycle of predator and prey populations. So it's often represented on the space trajectory graph because it gives a nice representation of how this is a cycle and how it does form a cycle overall. But yep, that's just kind of a lot of the intuition behind these predator-prey system relationships. I don't have any practice problems for these ones, but it's just a good illustration of maybe how differential equations can be used in slightly more complex systems. All right. Now, we do have a little more time, so maybe one more practice doing a separable equation. Let's say we have y prime is equal to xy squared minus x. I'll give you a couple minutes to work through that. All right, let's go over this problem. So first off, on the right-hand side, we're going to factor out an x. And now we can clearly see that this is in fact separable. So now we have y prime over y squared minus 1 is equal to simply x. Now that gives us the equation that 1 over y squared minus 1 dy is equal to x dx. And we can go ahead and input. The right-hand side is easy. It simply becomes 1/2 x squared plus c. The left-hand side is a little more difficult. We're going to need to use a partial fraction decomposition. So that tells us that a times y plus 1 plus b times y minus 1 is equal to 1. So letting y equal to positive 1, we get that 2a is equal to 1. So a is equal to 1/2. Letting y equal to negative 1, we get that negative 2b is equal to 1. So b is equal to minus 1. Then our left-hand side becomes the integral of 1/2 over y minus 1 minus 1/2 over y plus 1, which is equal to 1/2 natural log y minus 1 minus 1/2 natural log of y plus 1, which is equal to 1/2 x squared plus c. Multiplying everything across by 1/2, I get that the natural log of y minus 1 minus the natural log of y plus 1 is equal to x squared plus c1. Now I can combine the natural logs on my left-hand side using one of my log rules. I know that if I have a difference of two logs, I can write it as the quotient on the inside. And now I can exponentiate both sides, so I get y minus 1 over y plus 1 is equal to c to e to the x squared. From here, it's really pretty difficult to simplify further. I mean, in theory, I can multiply across. So then I have y minus 1 is equal to y times c1, y plus 1, or we'll break it apart, times c2 e to the x squared, which is equal to y times c2 e to the x squared plus c2 e to the x squared. Then I can add 1 to each side, and I have y, and or rather, I'm just going to put all of my y terms on one side and all of my other terms on the other. So I have y minus y c2 e to the x squared is equal to c2 e to the x squared plus 1. Now I'm going to factor a y out on my left-hand side. So I have y times 1 minus e, or 1 minus c2 e to the x squared is equal to all this. Then I'll divide both sides by that value. So I have y is equal to c2 e to the x squared plus 1 divided by 1 minus c2 e to the x squared. And that would be my final answer. All right, well, that's all I've got for you today. So thank you everyone for showing up, and have a nice week.